Welcome to the course on 3G, 4G wireless mobile communication systems. In the last lecture, we were looking at analyzing the SINR, the signal to interference plus noise ratio in a multi-user CDMA downlink scenario. We said that the decorrelated 0th path of the desired user, who is the 0th user, can be expressed as follows. It can be expressed as having several components. The signal component corresponds to user 0, path 0. Then there is a several multi-path interference components from the desired users, and then there are several interference components from the interfering users, that is the multi-path components of the interfering users. So, there is a signal component and then there is a multi-path interference and a multi-user interference. Hence, the net signal to noise ratio now gets modified as signal power to signal to interference plus noise ratio. This is known as SINR, that is the signal to interference plus noise ratio. All right, and our aim was to compute what the signal to interference plus noise ratio looks like at the receiver. For that, we started with computing the multi-path interference from the desired user, and we said the multi-path interference is given by this expression over here, that is P naught over n norm H naught square minus P naught over m norm H naught 0 square. Then we derived the multi-user interference. The multi-user interference we said is given by 1 over n norm H naught square summation k equals 1 to k p k. So, you can see the powers of all the other users are contributing to the multi-path multi-user interference at the user. And finally, we put the multi-path interference, the multi-user interference and the noise together to derive the total interference, that is the multi-path interference plus multi-user interference plus the noise power to derive the total interference plus noise ratio. Now, we can write the signal to interference plus noise ratio. However, we also said that this is only corresponds to decorrelating with respect to one path, that is the 0th path. We can do it similar thing at the first path, similar to what we did in a rake receiver. We can also latch on to the path, because remember we can extract the different components. So, if we decorrelate with a lag of 1, we extract the path arriving with a delay of 1 chip, that is given as R1 equals H naught 1 S0 plus W1, where W1 is the multi-path interference plus multi-user interference plus noise, so on so forth up to RL minus 1. RL minus 1 corresponds to the lth arriving path, and we have this, and this is we said similar to the maximal ratio combining scenario, similar to what we also have seen in the rake. So, I can combine all these components using weights, that is H naught conjugate 0 divided by norm H R0 plus H naught conjugate L minus 1 divided by norm H into R L minus 1, and that is my net maximum or rake combined statistic. And we said that the net signal to noise power ratio for the downlink multi-user scenario can be derived using this expression. Let me just rewrite this expression again to go over some of the salient aspects of this expression. So, the downlink SNR for multi-user CDMA is given as, we are considering the desired user as user 0. So, desired user equals user 0. This SNR is nothing but n times norm H naught square P naught divided by summation k equals 0 to capital K P k into norm H naught square minus P naught summation I equals 0 to L minus 1 norm or absolute value of H naught of I to the power of 4 divided by norm H naught square plus sigma n square. Okay. So, this is the net expression for the SNR. Let us look at the terms in this expression, or look at the different let us look at the different components of this expression. The first component is this component, this is the power of the desired user, who is user 0, that is we are assuming user 0 is the desired user, we can do the same thing at user 1 and so on. This is the spreading gain, remember this is similar to what we had at requisition, and similar this is at the heart of CDMA. Each user SNR is enhanced by the spreading gain. Now, this component is interesting, this is norm H0 square, this represents, remember similar to maximal ratio combiner where we had norm H square times P, this represents the channel taps of the user, and this represents the multipath diversity. This represents, you can clearly see we have a norm H square, that is we are combining using the maximal ratio combiner, or combining using the RIC receiver the different multipath components, hence this yields multipath. This is nothing but multipath diversity on the CDMA in the CDMA system. Now, this component that you see over here, this component below that you see over here, this corresponds to multi-user plus multipath interference. This is nothing but multi-user plus multipath interference. Look at this, it has all powers including user 0 and all the rest of the users. Now, user 0 power is arising because of the multipath interference. The other users powers are over here because of the multi-user interference. However, they are suppressed by a factor of n, that is why you have an n in the numerator, and this is what we traditionally have in any communication system. This is the thermal noise or the additive white Gaussian noise. This is the thermal or additive white Gaussian noise. So, this is a very rich expression, it has several different components. I urge you to again go over this to understand it better. Remember, this is a fairly complicated expression, it has multipath interference, multi-user interference, thermal noise, spreading gain. So, there are a lot of aspects to this, and as you have seen the derivation also was rather complicated. So, I urge you to again go over this again so as to understand this better. Anyway, that is one of the factors of CDMA, because it is a rich interference based system. So, analysis of this is not as straightforward as some of the other communication system. It is a more mature and a more advanced wireless communication system. Alright, so I urge you to again spend some time going over these expressions. Now, let us move over to the multi-user CDMA uplink. We have looked at the downlink scenario so far. Now, let us go over to the uplink scenario. Uplink refers to where several users are transmitting to the base station, that is they are transmitting on the reverse link or the uplink. So, let us move on to the multi-user CDMA uplink scenario, where I am going to again draw a similar schematic diagram. I have a base station and there are different mobile users, that is user 1 or that is user 0, user 1, user 2. Now, each user is transmitting to the base station. This is the base station, each user is transmitting to the base station. However, the direction of transmission is towards the base station. Previously, in the downlink, base station is transmitting to the different users. Now, we are considering the uplink, in which different users are transmitting to the base station. Hence, unlike in the previous scenario where the base station sums up all the signals and transmits them towards the mobile users, here in this scenario there is no summing up. In fact, different users are transmitting their own signals, coded signals, and they are going to add up at the receiver. So, unlike the base station adding up and transmitting on the downlink, here the summing up is automatic, where different users are transmitting on the uplink, and what the base station sees is the sum of the different signals. Hence, as a result, each signal propagates through a different channel. So, user 1 signal propagates to channel H0, user 0 signal propagates to channel H0. This is a multi-tap wireless channel. User 1 signal propagates through a multipath channel H1, user 2's signal propagates through a multipath channel H2. So, each user signals propagates through his own multipath channel to reach the base station, and the base station, what the base station sees is the sum of all these received signals. So, if I were to represent these channels, we have user 0, his signal propagates through his multipath channel, which is H0 of 0, H0 of 1, so on up to H0 of L minus 1. User 1's signal propagates through his own multipath channel, which is H1 of 0, H1 of 1, H1 of L minus 1. I am assuming that the multipath, the lengths of these different multipath channels are constant, so as to simplify the expressions a little bit, but you can, without any loss of generality, you can assume that these different channels have different number of components, different number of multipath components, and the expression does not change. It is essentially the same. I mean, you can write an almost similar expression without any effort. So, similarly, user K, the user K signal propagates through his own or her own multipath channel, and the different components are HK 0, HK of 1 and HK of L minus 1. Hence, previously in the downlink, where we were analyzing the received signal at user 0, we had only one channel, that is H0 corresponding to user 0. Now, we have, because of the uplink, each user signal is traveling through his own channel. There are k different channels, that is H0, H1 up to H subscript k. So, there are k plus 1. In fact, considering 0 as the desired user and 1 to capital K as the interfering user, there are now a total of capital K plus 1 different channels through which these signals are propagating. Hence, everything essentially remains the same. The uplink, now if you consider the 0th user as the desired user and we try to do the decoding, let me write down the expression for the downlink SNR and show you how it is modified for the uplink SNR. Or let us go back to the expression that we have over here. Now, here all the powers of the multi-user interference are multiplied by norm H naught square, because there is a single channel. Now, the only change that is going to come in this expression is that now each user's power is going to get multiplied by his own channel, that is norm HK square. Hence, the essential SINR for uplink multi-user uplink SINR is given as follows. The SINR equals n norm H naught square P naught. This is the signal power, there is no change in this. In the denominator, however, now I have sigma k equals 0 to capital K P k norm H k square. Now, remember previously this was P k norm H naught square was common, that is why we had sum of powers. Now, each power is multiplied by its own channel, because this is uplink and each signal is traveling through the channel corresponding to that user, and essentially the rest is all same. P naught over norm H naught square summation d equals 0 to L minus 1 magnitude H naught d to the power 4 plus sigma n square. This is the uplink SNR. As we said, this is the uplink multi-user. In fact, this is the uplink multi-user. CDMA SINR, and what we are saying is essentially everything remains the same as the downlink except this factor over here. Previously, where we had Pk, the power of the kth user is multiplied by norm H naught square, because all this composite signal is travelling through the channel corresponding to user 0. However, now each signal is travelling through the channel of corresponding user, hence Pk, the interference, is nothing but power times the norm of the channel of that user. The rest of the components are the same, that is, we have an n spreading gain, which is norm H naught, n is the spreading gain, norm H naught square is the diversity gain corresponding to user 0, P naught is the power corresponding to user 0, sigma n square is the thermal noise, everything except this factor here, that is Pk norm Hk square, that is what changes in the uplink. Hence, now we have analyzed both the scenarios, that is the CDMA multi-user uplink SNR and the CDMA user downlink SNR. Hence, now we have a very rich and a very convenient handle on what is the SINR, or the signal to interference plus noise ratio seen by a user on the downlink as well as an uplink in the CDMA system. Now, however, let us go on to the last topic that we are going to look at in CDMA, which is a slightly tricky topic, which is let me first talk about it briefly. This is known as asynchronous. This is known as asynchronous CDMA. What is asynchronous? What is the meaning of the term asynchronous? Now, let me go back to the same figure that I had for the uplink, multi-user CDMA uplink, and we said here that different users are transmitting to the base station through different channels. Now, previously what we have assumed is that when the base station transmits a composite signal, and it is also correct in the sense that since the base station is transmitting the composite signal, it is adding all these together synchronously, that is, it is aligning, that is, if I were to explain it technically, let us look at first synchronous CDMA. In synchronous CDMA, I take the signals of different users and I align let us say these are the codes of the different users, these are code 0, these are code 1. I align the edges, look at this, look at what I have over here. I have the edges aligned. I have the CDMA code sequences, the code sequences are aligned. What that means is the base station aligns this, multiplies the symbols, sums this up, transmits them in the downlink. That is possible because base station is transmitting the composite signal. However, if I look at the uplink, because each user is transmitting his own signal and each user is at a different distance from the base station. For instance, user 0 is at distance d0, user 1 is at distance d1, user 2 is at distance d2. Hence, and further each of these users is moving in the cell. Remember, we are talking about mobile wireless communication systems. So, what happens is as the distances are different, the propagation times are different, hence the chip sequences that are received at the base station are not aligned in the uplink. This is known as the asynchronous CDMA or asynchronous nature of CDMA. So, while user 0's chip sequence might arrive as follows, because of the random delay in the system, the user 1 chip sequence might arrive as with a slight delay. So, if I look at this, that is the arrival of user 0's chip sequence and user 1. So, this is the chip sequence of user 0, this is the chip sequence of user 1. On the uplink, there is a delay, and this delay is varying because of the mobile nature of the different users. So, this delay, which means that the edges are not aligned, this means that the codes are not aligned, that is the codes are now no longer aligned. This is known as the asynchronous, this is known as asynchronous CDMA. This is nothing but asynchronous nature, that is because it is they are not the code sequences, the edges are not synchronized. So, this is the asynchronous nature, and this sort of a CDMA scenario is known as asynchronous CDMA, and this is particularly known as asynchronous CDMA. This is known as asynchronous CDMA, and one of the remarkable aspects of CDMA is that CDMA can work perfectly well without synchronization. So, unlike TDMA kind of GSM issues, if you look into GSM, where GSM, well, the time slots, the different users have to be transmitting and have to be precisely aligned, otherwise there is going to be a problem because the user signals are going to interfere with each other. In CDMA, we are going to see shortly. In fact, it should be rather obvious, because in CDMA each signal is being transmitted on a different code, and shifted codes are also orthogonal to each other, synchronous or asynchronous. Shifted codes are always orthogonal to each other. Hence, remarkably, in a CDMA uplink, even if the users are asynchronous, that is the chip sequences are not synchronized, it is still possible to recover the signals of the different users. Hence, that is one of the other big advantages of CDMA, which is it makes possible asynchronous operation, and that makes reception and receive processing so much more easier in a CDMA system compared to 2G technology of TDMA. So, let us briefly look into asynchronous CDMA. As I said, asynchronous CDMA refers to the paradigm where these different chip sequences are not synchronized with each other. So, let us consider the code sequence C0. So, I am going to draw here the code sequence C. I am going to draw here the code sequence this is, let us say, code sequence C0 of user 0. Now, let us consider an asynchronous situation. The code sequence 1 of user 1 is slightly delayed with respect to user 0. So, because of the asynchronous nature, this code sequence of user 1 is slightly delayed. Let me illustrate it a little more clearly. This is slightly delayed this is the code C1 of user 1, and previously where they were exactly synchronized, now look at this, there is a slight delay between these code sequences arising because of the asynchronous nature. Delay because of the async nature. Now, look at this, when I correlate this sequence, let us say I am looking at the correlation of C0, C1. Now, because this C1 is shifted, part of the sequence C0 is correlated with the shifted C1 sequence, shifted by 1 unit. Part of the C0 sequence is correlated with C0 itself. So, what I am saying is I can write this correlation. Let me denote the asynchronous correlation now between, remember we were using, let me refresh your mind about this notation, this is user 0 user 1. This is the cross correlation between user 0, user 1. This is the cross correlation between user 0 and user 1. However, now I have a superscript A, which denotes the asynchronous nature. So, this A stands for the async correlation. Alright. So, I have the same notation R01, which is the cross correlation between user 0 and user 1. However, I have an A in the superscript which denotes the asynchronous nature. Let me go back to the diagram. Let us call this delay a fraction f. I am going to call this delay here a fraction f, assuming that the total chip time is unity, is 1. This delay is a fraction f of the chip time. Now, if f equals 1, then this moves by 1 complete chip, hence again they are chip aligned. Alright, so R01 is again becomes synchronous. So, as R01, as the fraction f varies between 0 and 1 to different degrees of extent, when I correlate C0 and C1, part of C0 is correlated with the shifted C1 and part of C0, the code of user 0 is correlated with, because look at this, when we directly multiply these two, this part here multiplies with the shifted sequence, while this part here multiplies with the direct C0 C1, the direct C0 C1, or let us call it what we had previously. So, R01 of A asynchronous can be written as 1 minus f, that is 1 minus the fraction times R01 of 0 plus f times R01 of minus 1. Alright, so let me explain this. As a fraction, as this delay varies as a fraction of the chip time, as it varies between 0 and 1, correlation is 1 minus f times R01 shifted, that is no shift, that is this part correlates with C1 with no shift or the shift corresponding to 0. However, the part corresponding to f correlates between C0 and C1 corresponding to a lag of minus 1, that is the shifted code sequence C1. And this expression also makes that clear. For instance, if f equals 0, that is there is no delay, then this becomes 1 minus 0, that is 1 times R01 plus 0 times R01 minus 1, that is R01 of 0, which is the same as what we had before, that is the direct synchronized correlation. As f becomes 1, it becomes 0 times R01 0 plus 1 times R01 minus 1, which is R01 minus 1, which is the correlation with the shifted sequence. However, now as f is varying between 0 and 1, we have a combination of both. Now, let us try to understand the nature of this f. First, f is a random variable. Let me make that clear. F is a random variable. Why? Because the distances of the different users are random. Further, the users are mobile, so these distances are changing. So, this f is a random variable because we have no control over where the users are in a different CDMA cell. It can be described as a random quantity. Further, f, the delay is randomly distributed. So, it is randomly distributed in, there is no preference to one value, any one value between 0 and 1. So, f is not only a random variable, but f is uniformly distributed in 0 and 1. So, f is random and this fraction f is uniformly So, if I were to draw the distribution, let me denote the distribution of f by g f, or the probability density function of f by g f of f. This distribution function is nothing but this is the uniform distribution, that is uniform between 0 to 1. This is f, the random variable as a fraction, the delay as a fraction of the chip time, which is uniformly distributed between 0 to 1. Now, I want to compute expected f square, because I am going to use that in my later analysis. Expected f square, it can be shown, that is easily integral 0 to 1 f square g of f df, that is nothing but function times probability density integrated over 0 to 1, but g of f is nothing but 1. So, this is f square integrated between 0 to 1, this is f cube by 3 between 0 to 1, it is nothing but 1 over 3. So, expected f square equals 1 over 3. Now, if you look at this, f is uniformly distributed in 0 and 1. If I take 1 minus f is also uniformly distributed in 0 and 1, because look at this, look at what are the limits of 1 minus f. 1 minus f lies between 0 and 1, 1 minus f lies between 0 and 1. So, 1 minus f is also uniformly distributed in 0 and 1. So, let me write that down. 1 minus f is also uniformly distributed between 0 and 1. In fact, the same result as expected f square also holds for expected 1 minus f square. Hence, expected 1 minus f whole square is also equal to 1 over 3. Expected 1 minus f square is also equal to 1 minus 3. So, what we have established is there is a delay, there is delay to, if I denote by f the fraction of delay corresponding to chip time, this fraction f varies between 0 and 1, it is a uniform distributed random variable, and the expected value of f square and 1 minus f square is both 1 over 3. Now, as we have seen in asynchronous CDMA, the asynchronous correlation, now let us go back to our asynchronous correlation expression. Remember, we wrote the asynchronous correlation expression 1 minus f r 0 1 0 plus f r 0 1 0 of minus 1. So, the asynchronous correlation, let me write so, the asynchronous correlation is nothing but r 0 1 of a equals expected value of f, or expected r 0 1 a is expected f r 0 1 of minus 1 plus 1 minus f r 0 1 of 0. This is nothing but expected f r 0 1 of minus 1 plus 1 minus f, or expected 1 minus f r 0 1 of 0. This is nothing but expected, remember f, the fraction, has no bearing whatsoever on the random correlation. So, hence this can be split into two, these are two independent random variables, hence this can be naturally split into plus expected 1 minus f times r 0 1, or expected now, we know that both these quantities r 0 1 of 0 and r 0 1 of minus 1 are 0, that is expected values are 0. We computed this in the previous lecture, hence this expected r 0 1 of a is not. So, the average value of the asynchronous correlation is also 0, and that is to be expected because these are random sequences. You delay them by a slight amount, that is you make them asynchronous by a shift, then it correlates with, it is as if you are correlating it with a linear combination of two different shifts, and each of them has a correlation 0, hence the net expected value is also 0. However, when we look at the power in this, we find something interesting. So, similar to the power in the interference, let us find the power in the cross correlation, that is R01 of A square, that is nothing but expected f R01 f square R01 square of minus 1, that is f R0 minus 1 plus 1 minus f R01 of 0 square, and this can be expressed as expected f square. I am going to expand the squares plus twice f into 1 minus f into R01 of minus 1 into R01 of 0. This is nothing but expected f square R01 square of minus 1 plus expected 1 minus f square R01 square of 0 plus expected twice f into 1 minus f into R01 of minus 1 into R01 of 0. Now, I am going to write down or expand each of these components. Expected f square R01 of minus 1 square is nothing but, we know that f and R01 are independent random variables, hence I can write this as expected f square into expected R01 square of minus 1. Now, we have previously derived that expected f square is nothing but 1/3, and we know that expected square of the cross correlation is nothing but 1 over n, hence this is nothing but 1/3 into 1 over n, hence this is 1/3 of n. Similarly, the other component is expected 1 minus f square R01 square of 0. Now, 1 minus f, which is the fraction, or 1 minus the fraction, and R01, which is the cross correlation, they are both different independent quantities. So, this is nothing but, I can split this as expected 1 minus f square into expected R01 square of 0. This is nothing but expected 1 minus f square is 1/3, expected R01 square 0 is 1 over n, hence this is again another 1/3 of n. Now, I am going to expand out the final quantity, that is expected f times 1 minus f into R01 of minus 1 R01 of 0, which is equal to expected again f into 1 minus f of R01 expected R01 of minus 1 into R01 of 0. Now, further we know that R01 of minus 1 and R01 of 0, they are also both independent quantities because they are shifts of the correlation sequence, and this is nothing but expected f into 1 minus f expected R01 into minus 1 into expected R01 of 0. We know that both these quantities are 0, hence this is 0. Hence, this quantity that we have here can be simplified as expected f square R01 square minus 1, this is 1/3, expected 1 minus f square R01 square, this is 1/3, I am sorry 1 over 3n, 1 over 3n, and this last term here is 0. Hence, I can now write the power in the asynchronous term as expected R01 asynchronous square is 1/3 of n plus 1/3 of n is nothing but 2/3 of n. This is the asynchronous cross correlation variance. This is an important quantity. This is nothing but the asynchronous cross correlation. Hence, nothing essentially changes, except now look at the variance. Previously we had 1 over n, now that is reduced to 2/3 of 1 over n. Now, you can see the reason for this is intuitive, because as you shift the different sequences, you are increasing the randomness, because now each sequence is correlating, part of it is correlating with one sequence, part of it is correlating with shifted sequence. So, now you are increasing the randomness, the more the randomness there is, the better it is. Hence, the effective variance now decreases. In fact, asynchronous nature of CDMA results in decreasing the multi-user interference. Previously it was 1 over n, now it has become 2/3 of n. So, hence it is a rather strange result, but it is an intuitive result. So, now instead of asynchronization resulting problems, it sort of aids your reception by decreasing the multi-user interference. All right. So, now the SINR of the asynchronous uplink is given simply as follows. The asynchronous SINR is given as SINR equals, or let me write down the complete expression, norm h naught square p0. Now, remember we had sigma n squared over n, that remains, except wherever we had the multi-user interference, that gets replaced, the 1 over n gets replaced with the factor 2 over 3n. So, this becomes 2 over 3n norm sigma k equals 1 to k, or k equals 0 to k norm h k square p k. Look at, observe this factor of 2 over 3n arising from the asynchronous nature, minus 2 over 3 p naught divided by norm h naught square summation d equals 0 to L minus 1 h naught d to the power of 4 plus sigma n square. The sigma n squared factor does not change, that remains as before. There is a 2 over 3n, hence the net expression. So, the SINR uplink comma asynchronous, this is given as n times norm h square p naught divided by sigma n squared plus 2 by 3 summation k equals 0 to capital A norm h k square p k minus 2 over 3 p naught by norm h naught square summation d equals 0 to L minus 1 magnitude h naught d to the power of 4. This is the uplink asynchronous multi-user SNR. This is the uplink multi-user CDMA SNR. There is the uplink asynchronous multi-user CDMA SNR, where the different thing compared to the synchronous is this factor 2 by 3. This factor 2 by 3 arises due to the asynchronous cross correlation variance, where we have seen this, the is factor 2 by 3 arises due to the async cross correlation variance. This arises to the asynchronous cross correlation variance, and then that is the final last expression we are going to derive in this topic of CDMA. So, we have rather comprehensively covered CDMA. We started with CDMA system, orthogonal spreading sequences of Walsh codes. Then we looked at the advantages of a CDMA system, in which we said interference, jammer rejection, suppression of jammer suppression, and also interference distribution leading to graceful degradation. We have looked at the rake receiver resulting in multi-path diversity, and finally, we have looked at these expressions of the multi-user CDMA SNR, both multi-user downlink, multi-user uplink, both synchronous and asynchronous, and hence that comprehensively covers different aspects of a CDMA wireless cellular system or a code division for multiple access wireless system. Let us in the end do an example of a CDMA system. Throughout this discussion in CDMA, I have not done any example. So, let me do a simple example to illustrate a simple CDMA system. CDMA system example. So, let me consider a CDMA system with spreading sequences of length 256. So, spreading sequence n equals 256, that is the length of the spreading sequence. I am going to consider a 2 user scenario. Going to consider a 2 user CDMA scenario in which P0 equals P1 equals minus 10 dB, that is the powers in dB are minus 10 dB. The noise power sigma n square equals 1, the noise power sigma n square equals 1. I want to ask what is the bit error rate of this system. I am going to consider a simple CDMA system with 2 users, spreading sequence length n equals 256. The powers of the 2 users are minus 10 dB, sigma n square equals 1. What is the bit error rate? First thing I am going to do is I am going to convert this powers from dB into linear. We know 10 log 10 log to the base 10 power equals power in dB, which is given as minus 10 dB. Hence, power is nothing but 10 to the power of minus 10 dB over 10 or 10 to the power of minus 1 equals 0.1. Hence, minus 10 dB power corresponds to linear powers P0 equals P1 equals 0.1. Now, we know that the signal to interference plus noise ratio SINR in a CDMA system is nothing but n times P0 divided by P1 plus sigma n square. This n, this is the spreading gain, this P naught is the desired user power, this P1, this is the interference user power, and this is the noise variance or the thermal noise. This is the noise variance. We know there is different quantities. N is nothing but the length of the spreading sequence, that is the spreading gain, which is 256 times we said P0 is minus 10 dB equals 0.1 divided by P1 is also 0.1 plus sigma n square is 1, hence this is 25.6 divided by 1.1, and we said the bit error rate is nothing but the BER is nothing but Q square root of SNR equals Q square root of 25.6 divided by 1.1, which is 7.02 into 10 power minus 7. Hence, we can see that at a power of minus 10 dB itself I am able to achieve a very low bit error rate of 7.02 in 10 power minus 7. If you look at an AWGN channel, we know that the power or SNR required for a bit error rate of 10 power minus 6 is roughly 13.6 dB. However, here we are able to achieve the same bit error rate at a much lower power of minus 10 dB. So, where is that remaining 24 dB, that is 13 dB minus 10, which is 13 plus 10, which is equal to 23 dB. Where is that 23 dB gain coming from? That is coming from this CDMA spreading sequence, that is coming from the remaining gain is from spreading, is from the spreading gain. If you look at this expression, I have this spreading gain that is causing this enormous huge 24 dB gain, which helps me achieve a bit error rate 10 power minus 7 even with a transmitter power of minus 10. So, traditionally, so if you look at CDMA wireless systems, you have them operating at very low EB to NO, or what is known in this case as EC to NO, that is energy per chip to noise power spectral density ratios. So, at minus 10 dB you can already get a bit error rate of 10 power minus 7 because it is a spread spectrum technology. All right, that is what we said about CDMA system. So, this is a very simple example, and now you can work on other examples related to multi-user downlink, uplink scenarios and the asynchronous scenarios. So, in the next lecture we are going to start at this point, summarize CDMA and move on to the next topic in our 3G 4G wireless communications course. So, I will end this lecture over here. Thank you very much.